Alrighty, in this lesson we are looking at how to solve systems of equations algebraically by using the elimination method. So there are other ways to solve systems of equations algebraically. We've seen substitution. Elimination we're going to be using today. It's kind of a really nice way once you get the hang of it, and it's often quite a bit quicker than substitution. Question number 1 over here is a really, really good candidate for using the elimination method. First of all, there's kind of 2 reasons why. Notice that, these 2 equations, I've got an xy in the first equation, xy in the second equation. So I need to do some kind of trick, some kind of thing to use both of these equations, because I cannot just solve a single equation with an x and a y. So the first thing that makes this really good for elimination is the fact that my x's are lined up, my like terms x's are lined up, my y's are lined up, and my just plain old constant numbers are lined up. That's the first thing that makes it really good for elimination. The second thing that makes it really good for elimination is the fact that on one of my variables, I have the same number in front with opposite signs. The -2 and 8, they do have opposite signs, but they're different numbers. This -4 and +4, they are perfect. We are ready to go for elimination. Now, all you got to do for elimination is this little trick that you're allowed to do, where once I'm lined up, I can add or subtract these 2 just down the line with my like terms. I really prefer adding whenever I can, and in this case, it works out that I add because I have a -4 here matching with a +4 over there. And you'll see why I even want to be doing that in the first place, why that negative of the same number makes it a good candidate. So when I decide to add these 2 together, the -4x plus 4x, a -4 plus a 4, they actually cancel out. It becomes 0x, but that's just nothing, right? That goes away. -2y plus 8y gives me plus 6y, and -12 plus -24 is going to be -36. Now, here's why this makes it such a good candidate for elimination, because look what happened. When I got rid of the -4x and put it with the 4x, I got rid of it, right? I can really write this again. 0x is just 0. 0 plus anything, it just goes away, right? That's gone. 6y equals -36. And just by doing this one step right over here, we already got to an equation with only one variable that we can solve for, right? With substitution, there's so much more work that needs to get done. We have to solve a whole variable by itself, then you plug in, you substitute, then you do all this other stuff. Here, we did one addition because we had our signs set up, and it canceled. I already have an equation that's one step away from being solved. So let's finish this up. Let's solve for y. I'm going to divide both sides by 6. Y ends up becoming -36 divided by 6 is -6, and that is the first half of our solution. What I've got to do now that I found y is just go back to the top and plug it into one of these 2 equations. It does not matter which one. I don't know. I'll do the first one. It's got smaller numbers. It really doesn't matter. -4x minus 2 instead of y. I'm going to put -6 in its place equals -12. Alrighty, and now I have one variable. I can solve this, right? -4x plus 12 equals -12. I'm going to subtract 12 from both sides. I end up with -4x equals, that was a -12 minus 12 more, -24. And I'm just going to run out of space here. Divide both sides by -4 to finish solving for x. X ends up being equal to 6. 24 divided by 4 is 6. So now we've got our full solution over here. And I'm going to write it as a set of coordinates, as I always should once I get a solution to a system. And so that is 6, -6 as my final answer over here. So that was our first example of how to do solving systems of equations by elimination. Let's try and run through 2 more examples that show just a couple different tricky ways that you might see this. Question number 2, looking over here. It's another good candidate for elimination. Not as perfect as this first one because, well, my variables are all lined up, so that's pretty good already, right? X on top of X, Y on top of Y, constant on top of constant. But here, my two variables that have the same coefficient, they're not opposite signs. There are two ways you can do this. The first way could be just to say, hey, I'm going to subtract the bottom one from the top one. I find that a lot of students get kind of confused with that. So instead what I like to do is just distribute this -1 in so that I'm switching the signs, right? I want two variables with the same coefficient but opposite signs. So I'm going to distribute this -1 to everybody here. So it's going to end up giving me -8x minus 2y equals -30. And now that I've done that, I can just add straight down, right? Now, I get it. Subtracting like 7 minus 8, 2 minus 2, 24 minus 30 is the same thing as adding them. But I just find that students tend to make a lot less errors when they do the distribution of that -1 first and then they add straight across. So it's looking a little confusing. I'm going to bring this guy down here just so we can see exactly what's going on. 7x plus 2y equals 24. I was just bringing this guy down here so I'm not like adding over this line that I've already used. So let's do it. -8x plus 7x is going to get me -x, right? It's a -1x, but I can just leave that as -x. The whole reason we multiplied by this -1 to both sides was so that I have these two signs be opposite. Once the two signs are opposite with the same coefficient, they get canceled out. Good. Over here, -30 plus 24 is going to end up being -6, and I'm almost done. If -x is equal to -6, well, all I got to finish up by doing here is divide both sides by -1. It'll cancel that negative sign there. X is a +6. Oh, look at that, just like the last question. But we're not done yet. We got to take this 6, plug it back into one of my two original questions. Doesn't really matter. I'll plug it into this first one. So I'm going to come back down here. I'll rewrite the question. 7 instead of x. I know that x is now 6, so 7 times 6 plus 2y equals 24. 7 times 6 is 42 plus 2y equals 24. And at this point, we can just go on solving it, right? So subtract 42 from both sides. Uh-oh. That is not super pretty. 24 take away 42 is going to be... Let's just confirm that with a calculator. Ooh, sorry, I hit the camera. 24 take away 42. Okay, -18. Always good to be 100% sure that you're getting it right. Finish up by dividing both of these sides by 2. We end up with y is equal to -9. That's the second part of my solution. So my final answer is going to end up being 6, -9. This is where these two original equations would intersect if you graph them at the point 6, -9. So that is our solution. Alrighty, final example that we're going to do in this video. Tiny bit trickier, but really not that crazy. So once again, you know, this is looking a little bit worse, right? Here, this first one, we're all lined up. Second one, we're all lined up. Third one, we are all lined up. But in the first one, we had same number for one of my variables, different sign. Second one, I had same number, same sign, so I just had to fix that by multiplying by a -1. Here, none of my numbers are even the same. And, you know, maybe you start thinking, well, this x is kind of by itself already. Maybe I just move that 3y over and just do substitution method. And if you prefer substitution method, go for it. But let me just show you how to deal with this type of question by using elimination. So what you got to do is choose which variable you want to eliminate. Do we want to get rid of the x or do we want to get rid of the y? I'm going to say I'm going to get rid of the y in this question. Don't ask me why, just, that's a bad joke. Don't ask me why, just, you know, that's what I chose. And so now you got to look at, okay, I have a 9y and a -3y. What could I do to both sides of this equation to get this number in front to be the opposite of that number, right? Same number but opposite sign. So I know, well, hey, if I take negative 3 and multiply it by 3, it would give me a negative 9, and those would be ready to cancel. So you can do exactly that, right? As long as you're multiplying the same thing to both sides, it is okay. So I'm going to multiply this 3 to the left side, it distributes. I'm going to multiply this 3 to the right side, it just multiplies. And let's take a look. So I'm going to end up with 3x. The 3 times negative 3 is going to get me a negative 9y, and that's why we chose to multiply by 3, so that these two would match up, right? The hardest part of this question now is figuring out what do I need to multiply both sides by to get two numbers ready to eliminate each other. And then the negative 6 times 3, negative 18. And now I have a 9y and a negative 9y. I can add these two together to eliminate the y's, and I'm pretty much, halfway done with the problem at that point. Again, I'm just going to bring this down just so it doesn't look, it's not too confusing when I'm adding. Negative 4x plus 9y equals 9. I get to add them together because I have the signs being opposite. That's kind of nice. 3x plus negative 4x is going to get me, again, a negative x. This negative 9y and positive 9y, they cancel. We designed it that way, right? That's why we chose that 3. And then the negative 18 plus a positive 9 is going to get me negative 9. If I have negative x equals negative 9, that means that positive x is going to be positive 9. We are almost there. Take this, plug it into one of my two original equations, and we're good to go. I'm going to plug it into this second one. So instead of x, I'm going to put 9 in its place. Minus 3y equals negative 6, right? I was just copying that second equation, but plugging 9 in place of x. And we're getting there, right? Subtract both sides by 9. I'm going to have to rewrite this up here. Sorry, I'm running out of space. So I end up with negative 3y equals negative 6, take away negative 9, negative 15. Divide both sides here by the negative 3. And we end up with y is equal to 5. And so at this point, we have our two coordinates needed to get the full, the x and y parts of the coordinate to get the full answer. So I can say here that the final answer here is 9, 5. So those are 3 examples of how to do systems of equations. I guess I'll leave it on the answer for a second. How to do systems of equations by the elimination method. Yeah, hopefully that was helpful.